Thank you very much for the kind introduction. It's a great pleasure to be here. So yes, I'm going to be talking about creating next-generation quantum networks. In 1969, something monumental happened. The first message was sent via the internet. It was very small at that time, just 4 nodes connecting different parts of the United States. If we jump forward to 2011, this image here shows global connections. The different colors represent the connections between different countries and continents. You can see how much it's changed and grown, and we know how much of an impact it's had on our society. We're now witnessing the birth of the quantum internet. So what is this quantum internet? Well, instead of sending classical data using a classical computer, you send quantum data using a quantum computer. And instead of using a classical bit, which can either be a 1 or a 0, and this is how you encode your information, you can use a quantum bit or a qubit. The interesting thing about this is that it can be a 1 and a 0 at the same time. And that means that a quantum computer can be incredibly fast. So with a classical computer, the power scales in a linear fashion with the number of bits that you have. But with a quantum computer, it scales in an exponential pattern. So I'd like to give you an example of what that can do. So say you want to talk to your bank. You want to do this securely and privately. And the way that we do that is using encryption keys. Say that you had a 2048-bit key. If an eavesdropper is listening in, trying to get your data, and they had a fast computer, it would take them around 317 trillion years to break that encryption. If they had a quantum computer, however, that would take just 10 seconds. You can see what impact that has on data security. But quantum offers us something else, and this is called quantum key distribution. Because of the laws of physics, it's impossible to break that encryption, even if you have a quantum computer. So if you want to create a network of secure nodes across a country, what might that look like? In 2020, BT implemented the UK's first quantum network, and it will expand. So what might that look like? Well, you'll have trusted nodes across the country with metropolitan links and then local links to those metropolitan links, with satellite stations for trusted data transfer. And what do you need from this technology? Well, you need to be able to send these quantum keys over a long distance. You need it to be reliable. And you need to integrate the technology into our current communications sector, as that's still going to be in place. And you want it to be cost-effective. So where are we with the technology? You can break quantum into 4 generations. We're currently completing generation 1 and entering generation 2. In generation 1, we showed that it works, which is wonderful. And it's really, people are starting to see what it can do. However, it's still expensive, and the distance over which you can send those keys is still somewhat limited. As we're entering the 2nd generation, the cost is coming down, and that's because there's more and more players in the field, and this supports our mass manufacture. Also, the technology is constantly improving, so we can send those keys over longer and longer distances. As we enter generation 3 and 4, this is where we see the true birth of the quantum internet. Instead of just sending these quantum keys, you can send true quantum data in real time. So what might generation 4 look like when we have a quantum cloud with native links to quantum computers? Say that you're a material scientist that wants to develop a new material to sequester carbon from the atmosphere, or you're a chemist and you want to invent a new and greener catalyst. Well, because of the power of the quantum computer, you can run very, very complicated simulations very quickly. And this means that we have the opportunity to design many more materials or catalysts to help the environment, say. So who are we? So we're a young UK startup, and we spun out of the University of Sheffield in 2019. Since then, we've been establishing ourselves in the UK quantum ecosystem. We're part of a number of UK government-funded collaborative projects. And earlier this year, we closed a 7-figure seed round to bring our technology to market. So we're a hardware company, and so we're developing the building blocks for this quantum key distribution. So one of the ways that we can make these building blocks is using photons. You encode the information within these photons, and they can travel this long distance. The way that this is currently done is often using attenuated classical light sources so that you just produce one photon at a time. However, our technology instead uses a true quantum light source, or single photon source. The benefit of that is that you get a very high quality output. It's deterministic, so every time you trigger, you just get you get a photon, and all of the photons are indistinguishable or identical to one another. And they're high purity, so you just get one photon and nothing else. So really the benefit of using this technology is the high quality that you get. So very briefly, for those of you that are interested, this is how it operates. You take a quantum dot, which is a nanocrystal that can produce these single photons of light, and you embed it in a semiconductor nanophotonic structure, which acts sort of like a resonator. You then have a laser input, and your output are these single photons, which you use as your qubits. So the benefit of using semiconductor is that it's scalable. And we want this scalability because if we want to go from where we had the 4 nodes in the classical internet to this fast connectivity, we want to scale up the number of qubits we have. And we can leverage the silicon sector, so we have so much know-how there that can be applied to our semiconductor platforms and really assist in this mass manufacture and scalability. So this area that I've been discussing is called photonics, which is all about light. So as we saw, we have applications in communications and computing, and also in quantum sensing. This is where you use a quantum property object to probe a physical property on a scale that you wouldn't be able to with classical. So an example of this could be high-resolution brain mapping. But back to communications and creating these networks. Well, as I said, scalability is incredibly important. So what else do we need? Well, we need our technology to be modular, and that's so that it can integrate in with the current communication technology, the classical technology. We also want it to be plug-and-play and fiber-based, and this makes it user-friendly and assists with uptake. It's a very exciting time for quantum. We're seeing more and more companies pop up and events like this, and quantum's really entering the media and public sphere. Governments and industries are really seeing the potential and what it could bring. And this is reflected in global government spending, which has increased 20 times over the past 5 years alone. So we really are entering this stage of accelerated growth, but we can go further. I'm very excited to witness the quantum internet become a reality and see it change the world to an even greater extent than the classical internet did. Thank you.
Thank you. Thank you, Ms. Ovenden.